Welcome to another video. Our previous video introduced model fit as a way to assess how well the model is performing and how trustworthy it can be. In this video, we're going to introduce some more formal steps that you could take to validate your model, which is just another way of saying proving that your model is worthwhile enough to take its conclusions seriously. And the main reason that we need to do this is if we're using the model for identification, then we need to make sure that the model is working properly in order to make the leap from the model to real-world policy conclusions. We'll add a little bit of formality to our discussion of model validation and then go through some examples of real-world papers and how they have done this. The main idea with model validation is trying to convince skeptics that the model is actually a reasonable representation of reality. And one issue that some people have with structural modeling is that if you're using the entire data set for estimation, then you could overfit the model, meaning that the parameter estimates would not produce data in a more general setting than the exact data set that was given the model. We can also be overfit if we're only matching on the targeted moments. So another way of saying that the model is overfit is that it only fits well on moments that it directly targeted and it fits poorly on other moments of the data. And so the whole idea with model validation is that we want the model to be generalizable to other contexts than just the one that it was estimated in. And this is particularly important because we're making some assumptions to produce counterfactuals. And one of those assumptions is that the parameters are going to be invariant in the new environment that we simulate. So what would a valid model look like? Well, it would be able to reproduce patterns in a holdout sample that was excluded from estimation, and or it would be able to match moments of the data that were not explicitly targeted as part of the estimation. So these are kind of the two ways that you can level up your model validation from just showing that the model reproduces your Y variable on average, which is what we talked about in the last video. More broadly, validation just means, does this make sense? Is this reasonable? It can be qualitative in the sense of, do the parameter estimates conform to economic theory? If I'm getting a coefficient on price in a demand estimation problem and I get a coefficient that's positive, that would not conform to economic theory, for example. It could also be quantitative in terms of, is there a low enough prediction error if I take the model and try to reproduce data with it? Is it very close to the actual data that I'm using? And if you've had any experience with machine learning, there's a notion of cross-validation, which is a way to show what the right level of complexity in the model specification is for accomplishing the task at hand. And this cross-validation idea from machine learning basically enables the computer to automatically search for the best specification. And in structural modeling and structural estimation, we don't typically do automated specification search because estimation is not as trivial as it is in some common machine learning contexts. So if you've heard of that notion of model validation, I wanted to just kind of make a brief contrast between the machine learning approach and what we've been doing in this video series. So let's look at a paper by Lang and Palacios. This is unpublished. It was released several years ago, but I still think it has pedagogical value for understanding when we might want to think more about model validation and be more formal. So the key question of this paper is, how do we know the amount of unobserved heterogeneity that we should allow our model to have? In this case, it's a finite mixture model. Basically, the question is, how many unobserved types should we have in the model? We don't know upfront how much there should be, and the typical approach is to add enough types so that you get good in-sample fit. And so the authors of the paper, they go through these exercises where they're searching for the optimal number of types, and they have some metrics that they use that are commonly used in statistics to quantify when the optimal model has been found. And what they're doing is they're using a 20% holdout sample for assessing the model or the fit of the model, and then they're estimating the parameters of the model on the other 80%. And then they rotate through which chunk of the data is held out and which one isn't. So that's a very common approach in machine learning. And then basically they're formally comparing the fit, like I just said, using some commonly used metrics and statistics. And the main takeaway from their paper is that just visual in-sample fit metrics are not going to be good enough because it's going to perform poorly in this holdout sample unless you have a greater degree of heterogeneity in the estimation. Let's move on to another paper. This is by Delavand and Zafar, published in 2019 in the Journal of Political Economy. They're looking at validation slightly differently. They're wondering if treatment effects can be predicted using just the control group. And their model has to do with what we'll cover in our next video series, which is stated preferences. But basically, they specify the survey respondents to think about different states of the world, and they're just comparing model predictions across those states of the world. And so there's a new state where there's basically free schooling, and the original state has the schooling costs that are in the world today, and they get preferences under both of these regimes, and then they estimate the model using only one regime, and then use the other regime as a validation. And because their model performs well in this validation regime, it's a good model, it's credible. That's one of the main reasons it's published in one of the top journals, Journal of Political Economy. And then a third example is one that we've gone through in a prior video where we talked about school choice vouchers in India. So in this paper, they used a field experiment to assist in validating their structural model. They estimated their structural model only on the control villages, basically what someone would do if they didn't have any experimental data at all. And then they tried to use their estimated model in the control villages to predict what would happen in the treatment villages. But in this case, because they had the experiment, they could actually see what happened in the treatment villages to actually see how good their model was. This is normally not possible because normally we don't have experiments that we can rely on for any question that we're interested in. And they found that their initial attempt at the structural model had a few shortcomings. And so they used this opportunity to beef up their model and make it more realistic, and then found that their enriched model predicted outcomes in the treatment group much better. And then they can use their enriched model to do the policy experiments that they're after, which, if you recall from that video, they were really interested in estimating the marginal value of public funding, which is just, does this program pay for itself relative to the surplus that it creates? So that is a little bit about how we can more formally validate our model. I would say that these types of validation attempts are not always feasible for all structural models, and so you won't always see these steps taken, but every complicated structural model does need to undergo some amount of showing the reader that the model is valid in order to have a basis for understanding how reliable the counterfactuals are going to be. Up next, we'll walk through how to do the counterfactual policy simulations. So I hope to see you there.